All right, so the plan today, I just want to finish off about the self-balancing tree, especially how to do rotations. I also definitely want to review a little bit about deletion, how you can delete from binary search tree. There will be actually several cases we're going to consider. And then we'll do the more like a simpler rotation after deletion, and then I can save a little bit more complicated one. Maybe for Friday, we can do some tutorial exercise together. I also want to show you some programming exercise as well this Friday. So it's going to be in person. I'm going to hold it myself, so make sure you come. And then next week will be lecture number 8. So we got 8, 9, 10, and 11 before the reading week. So my plan is to start about a graph. From lecture number 8. So that's going to be new for everybody. So I want to cover, first of all, it's going to be a very long lecture. There are many things about graph, really. Primarily, this course will be lots of many things about graph. So I'll do the 4 lectures just to cover the basic and also talk more about how you can implement a graph. So when I release the assignment in the beginning of the reading week, you will actually get some hands-on to actually do. Okay? So that's kind of the plan. So today, we just see how much we can do to finish off the self-balancing tree. But it's not too many things left conceptually. We just want to go over example together and make sure you guys are comfortable with it, especially for rotation. Okay. So let's now recap very quickly from last time, and then we'll continue with the exercise. So last time, we basically talked about how you can implement binary search tree, and of course the most basic unit on the binary search tree is a node, right? And the node is going to be connected by having parents, it's going to be connected by having parents left and right, and also the key for searching purpose, and also the data value. We don't really use the value really for anything substantial, right? It's only for storage. Storing something like a useful. But for the parents, left and right, and also, so these 3 things will be important when you do rotation. So when we do the graphical example in the class, we wouldn't dive into details about how the parents, left and right should be set exactly, but that's something we need to work out the details. So in this Friday's tutorial, I'll give you some example about doing rotation. So at least you can get some idea. And then, of course, the key is really for searching, right? So we talk about the structure of the BST node. That's something we're going to stick to for this course. And then we spoke about how you can do search, do a binary search. That's really something basic from 2101, just about either go to the left or right, depending on how you compare the key value against the current key you're looking at. And there are 2 cases. Either you have found the key, for example, in this case, we have found 65. In that case, you simply return this internal nodes. And then maybe after that, you want to replace its data value, for example. Right? You don't really change the key once you have found it. On the other hand, I'm looking for this key here, 68. It doesn't really exist. However, the return value is going to be an external node in such a way that if you put this non-existing key right here, it's still going to preserve the in-order traversal once you get a sorted sequence from there, right? That's very important insight that we went over, right? So there are 2 cases for search. And then, so this one here, just an example code about how you can do binary search on the tree. And you can also look at the slides, which I didn't really show here on the iPad, also about how you can implement binary search on the tree. That's also very straightforward. So you want to go over this code here and also make sure you understand when we try to search something that exists, it's going to return some node reference. For example, the reference to this internal node, if you have found the key, for example, 28. On the other hand, if I want to search for 23, for example, so 23 doesn't really exist right here, but it's going to return this particular node, external node. Not this one here, not this one here, not this one. Because if you somehow put 23 here, currently doesn't exist. But if you did put it there, hypothetically, if you do the in-order traversal, it's going to be 21, 23, 28, and then this one here, right? So the in-order traversal is still going to give you the sorted sequence for the key. That's so important to see which external node is going to return. So I would say when you review the code example, pay more attention about these 4 assertions, right? Just about which one should be returned. And then we spoke about this important facts about binary search tree. And we're going to use these facts today when we talk about deletion in the more tricky case. It's not a tricky, but once you understand. So you got some parents, left child, right child, and the subtree rooted at left child can be arbitrarily complicated, and similarly for this one here as well. So we talk about the different nodes, the leftmost node, which is the minimum key, on the left subtree, and also rightmost node, which is the maximum in the left subtree. And then we'll try to see what's going to be the order for in-order traversal, right? So that's the order we talk about, right? So knowing the minimum and knowing the maximum is good, right? That one's kind of straightforward. But to really know about the role of this N2 here is very important. If you somehow look at N2 here and also the P here, if you look at that diagrammatically, it seems like they're quite far away from each other. But if you look at a sorted sequence, they're simply next to each other. It's simply because when you do the in-order traversal, once you're done with this, you're going to go here right away. Right? So I assume you're kind of familiar with the in-order traversal. If you're not exactly sure how to do in-order traversal, you may want to review this part here, maybe from 2101, or you can just reach out to me. That part, maybe I wouldn't review explicitly in the lecture. Okay? But just to be sure you know about the in-order traversal between these three, right? After P, also you're going to go directly to right here, the N3, the leftmost, which is the minimum in the right subtree. Okay? And we'll talk about the interpretation for each. And these two nodes are very important for you to really do some replacement after you have removed some nodes from the binary search tree. That's something we'll see today. All right, so talk about insertion. If you try to insert some key that already exists, you find a key, you find an internal node, and then simply replace the data value. And we don't change the key. Okay? On the other hand, you're trying to insert into the tree, let's say 68. And 68 currently does not exist. And it's going to return this particular external node right here. So what you would do is you're going to set the left child of this node here. Currently, it is this external node. But you're going to replace it by some internal nodes and set it to be the key and also data value you're inserting. Right? So that's conceptually the idea. You may want to think about how would you implement this in Java, right? So that might be something you want to think too. Okay? That's about insertion. And of course, what we said later in the lecture on Monday was after the insertion, your tree balance may or may not be maintained for the heights. So that's why rotation may be necessary. Okay? So that's something I'll recap as well. So we talk about rotation in general, right? The most important thing for you to remember is before the rotation and also after the rotation, okay? Of course, the structure of the tree is going to look very different, right? For example, you can see B used to be here, but has now become the root right here, right? Also, if you look at the heights of the subtree, right, you can see we used to get some unbalanced tree right here, because you can see here for B here, is this node balanced? In this way, it is, because you can see H plus 1 and H, the difference is only 1. However, if you look at this node over here, you can see the height difference is between H plus 2 and H. So it's more than 1. So this tree here is unbalanced. After we kind of restructure the tree by doing some rotation around the middle node B, we're actually going to get something that's actually balanced, right? Just understand exactly how to understand this abstract rotation here. But we're going to see something concrete today for sure. And the second point to remember is, how do we argue that this rotation here is actually correct in the sense that it's not going to violate the search property for the tree? So if you look at the in-order traversal before and also the in-order traversal after, they are exactly the same sequence, just the same. It's just the way you kind of structure around the root is different. But the good thing is, this after the rotation satisfy the height balance property. So we still get log n as the heights. If you don't do this rotation here, after the insertion or deletion, you might just end up having heights gradually towards linear as opposed to log n. Right? That's why doing rotation, it is so important to make sure you get it right in time. Okay? And the only rotation we did so far is about left rotation, right? We basically going to see left rotation, right rotation. You're also going to see left, right. You're also going to see right, left, right? So these are the four kinds. Okay, we're going to see the right rotation is very similar. For that one, I can assign to you as exercise. But today we can do the left, right as example. And then there will be another multiple ones we're going to do maybe in the tutorial session on Friday. Okay, we'll see. Okay, but let's just recap this one very quickly. So let's say you got A, B, and C. They kind of slant the same way right here, right? This all the way slant to the right, right? To the right. What we want to do is we want to somehow promote this B up to be the root. So you can see we're going to this direction here. So that's why we're saying that we're doing a rotation, left rotation on the middle node B. That's what we're doing. Okay, so that's why once you get a B promoted up to here, the root, A will be demoted down right here, right? And then C also will become also one of the subtrees, the root of the subtree, right, for B. And then, but the good thing is we still get the same in order traversal, right? You got T1, A, T2, B, T3, C, and T4. This sequence here will be the same before and after the rotation, right? That's always the key you want to remember, okay? Any question about this? We're good? Okay, so we'll review that again. When we try to complete the exercise, we'll do that. All right, so that's the last page I believe we had last time. We completed as well today in the beginning. So we said we actually got a sequence of keys to really insert into the tree. So what we got is right here, right? This one here, you can annotate the heights bottom up from the external to internal nodes. This tree here is balanced, right? So this one here, okay, let me just start with here, right? That's a new completed duplicate. So what we have is, for A here, it will give you a tree that's balanced, first of all, right? So this is a balanced tree. On the other hand, B here, after inserting 100, is going to give you something that's unbalanced. Unbalanced in the sense that if you don't really try to handle the unbalanced facts right away, you're gradually leading towards linear heights for your tree. Not necessarily right now, but in the long term. So you definitely want to handle that systematically. So after inserting 100, right, you can see 100 is right here. And then, so that will be the new node being inserted, and of course underneath it, you got two external nodes. And then we try to annotate the height bottom up again, right? For that process, I may not repeat. So you can see that right here. The height difference, you can see 0, 0, difference is 0. 0, 1, difference is 1. So 0, 2, over here, the difference is actually 2, right? So that's the first instance where we got the child node's heights will be more than 1. That means their parents, which is this node here, that's the very first node that's unbalanced. Okay, that's very important because you need to identify the lowest node in the tree that's actually unbalanced. Okay, so again, so you want to look at this node that's being inserted and follow along its ancestor path all the way to the root. And typically after insertion, you don't need to go that far. So it's not exactly log n for you to go all the way to the root, not necessarily. You might just want to go about 1 or 2 levels. It's more like a constant, okay? So once you go to identify this particular node here, that's be the lowest node that has the, I will make a quick notes here. So A here, this is the lower, oh, actually I wrote it last time, okay? The lowest node. The lowest node, that's actually unbalanced. That's the most important facts, okay? In the case of the insertion, we only need to do one single rotation. Well, the single rotation itself can be either double rotation or maybe single rotation. But when we do deletion, you may have to do more. That's something we'll see. All right, so that's where we ended up with, right? So let's now complete this, okay? So what we identified the other day was A, B, and C, right? So we got A, we got B, and then we got C, right? And then we got their subtrees, T1, T2, T3, and T4. And let's now remind us aside right away, and then we're gonna do rotation. So I'll put it here. So let's say we got A, and also we got B, and also we got C. Underneath A, we got T1. Underneath B, the left child, we got T2. And then we got T3 and also T4, right? That's what we have. What we want to do is we want to do a left rotation. We want to do a left rotation on B. So that means B is going to become the root right here. Okay, and then underneath it, we're going to get A here, and then we're going to get C here. And then we got T1, T2, T3, and T4. All right, you can double check. If you see the in order traversal for this one, T1A, you can see T1A, T1A, T2B, T2B, T3C, T3C, and then T4, right? Exactly the same sequence. So that's the right way to do. So you can always try to remind yourself before you actually do the concrete rotation. So just remind yourself how to do it. All right, so final step. I'm just going to just draw from scratch quickly, okay? So what I will do is I'm just going to put here, C. Okay, so I got 44 at the top, and then underneath it I got 17 and 78. And 17 has the external child here, and also we got 32. And then over here, okay, good. And underneath 78, I got 50. And then I got external and also external, okay? So think about this part over here is something I'm gonna change, this part here, okay? Just before I do that, let's now try this, okay? I'll use a slightly different color. So here I got 88, and then I got this. And then underneath it, I got 95. And then I got external. And then I got 100. And then underneath it, I got this. And underneath it, I got this. Okay? That's what I got. And let's now do the rotation. Okay? Let me just annotate one more thing, and then we'll do it. So this one here is basically A, B, and C. And here we got T1, T2, T3, and T4. Okay, how do we do the rotation? Somehow I'm using digital pages, so it's easier for me to do the illustration, but I'm gonna see how you can do that on paper. I'll let you choose whatever that works for you, okay? I'm just gonna set this aside. Okay, just this part here. All right. I know that, I know that I should really get B here. So B here is in the middle node. I need to get it right here. It's going to be the new root. And then underneath it, I should get A and C. I'm going to reconstruct the tree. I got A here, and I got C here. Okay, so far I have reconstructed only A, B, and C in this order. What I got left is T1, T2, T3, and T4. Right? I'm going to put them individually. So T1, T2, T3, T4. Okay, so I got T1 here, T2 here, T3 here, T4 here. So I got T1, T1, T2, T3, T4. Okay, so this one I don't need it. And finally, I can simply let this one here go back here. I'll put it here. And you can think about this part here, we'll just link to it. Like that. Follow? All right. Of course, you can draw better. I'm just running out of space to the right. Okay. And let's now double check. Is this tree balanced though? Right. We know that the in order traversal is going to work. What about the heights? So if you look at that, so let's see. We got 0, 0, 0, 0. 1 and 1, right? This will be 2. So here we got 0, 0, and then here we got 1. 1 and 2, we actually got 3, right? So 0, 0, 1, 0, 1, we got 2, right? 2 and 3, we got 4. Right, you can double check. The whole tree here, after annotation, is still balanced for every node. All right. Hopefully it's not too bad, right? Just get the big picture right. So usually it will be somehow either given a tree like this, or you got to reconstruct a tree like this, right? Typically, one way. And after that, I might ask you to really do some operation. Could be insertion, deletion, or maybe a serious operation, right? Let's say this, in this case, insertion. After that, you got to update the heights. You only got to update along the ancestor path of the node being added in this case. And you will notice you want to identify the very first node that has become unbalanced. And from there, you got to decide which pattern you're going to do. In this case, because they all slant this way, so you're going to do the opposite way for the rotation on the middle node. Right? That's what we got. All right. And of course, this part here is just a little aside. You can remind yourself. It's not really part of the answer, right? Just something to remind you right here. Any questions? We're good? Okay, so that's about doing some left rotation, okay? There is another case. I'll just talk about the general case. So this example here, I can let you try. I can tell you that for this particular one, after inserting 46 into the binary search tree, after you have constructed that, it's going to become unbalanced. But in this case, you only have to do a single right rotation as opposed to left. But I'll let you do this exercise. This one should be rather simple. I'll give you the solution. And just talk about this one very quickly, right? You can see the A, B, and C. If you recall, A is going to be the lowest node. That is unbalanced. Okay? The lowest node that's unbalanced. And they all slant this way. Slanted to the left, right? So what you really want to do is, I want to somehow do the right rotation to promote, to put B above, right? To maybe so that it becomes the root. And then put A and C under B as the left child and right child. Okay? So let's see how we can reconstruct it. So B is here, right? That's a middle node. So what we do is we'll try to do some right rotation. The right rotation on the middle node B. All right, so after that rotation, we're actually going to get B as the root, and then C and A. Why should that be C and A rather than A and C? It's because when you do the in-order traversal, you're going to get C and then B and then A. Right? So that's why you're going to get C and then B and then A. The order must be the same. And then underneath C, you got T1 and T2. Underneath B here, you should get T3, right? I'll just write it down. So here you got T1, and then you get T2. And then you get T3 over here. You can see T3 is in between B and A. So if I get T3 over here, it's also in between B and A. If you think about it in order traversal, right? Think about if you do in order traversal. After B, you're going to get to T3. And then after T3, you're going to get to its parents, A, right? And finally, you're going to get T4. So the in-order traversal, let's remind ourselves, the in-order traversal is really T1, T2, oh, beg your pardon, T1, and then followed by C, and then T2, followed by B, followed by T3, and then A, followed by T4. Should be the same, before and after rotation. So in the lecture, we're just going to show you how you can do this on the paper and make sure it's clear to you. And then in the tutorial today, we're going to do some hands-on stuff to see how we can implement rotation in Java. Okay, there'll be some fun stuff to really do together. Okay. Any questions about right rotation? Okay, so when you do this exercise over here, okay, so I can give you a little bit heads up. Okay, what you're going to see is, you can see in the previous example there, when you identify this lowest node that's unbalanced, you can see A, B, and C, they all slant to the right. So that's why you got to do the left rotation right here. So what you're going to see later, you're going to see A, B, and C is going to, A, B, and C will slant to the left. In that case, you got to do a right rotation for B, just the opposite. Okay, so that's something you got to remember. Okay. All right, if no question, why don't we do one more, okay? One more about insertion, and then we'll take a very short break, and then we'll do the deletion, okay? That's the idea. About insertion, there are two more rotations that actually is possible. And I would say there's something they call tri-node restructuring step, Okay, I'll write it down here just for your information so you don't really get confused. Trinode in the sense that we always got A, B, and C as a reference. Okay, it's called trinode restructuring. Step, because you always got A, B, and C. Of course, the B here is the middle node, right? So there are two cases. The restructuring step may involve only one single rotation. It could be just one rotation, which we have seen. Rotation can either be left or the right. Either left or right is simply because A, B, and C slanted the same way. Okay, that's what we have done so far. We can see another example there. The trinode restructuring step may involve two rotations. And the two rotations is going to be either right-left or left-right. We'll see, okay? I'll show you the one that's going to involve right-left. And the left-right will be something we can either assign to you or we can do in your tutorial. We'll see, okay? But they are done in a very similar way. So these two are the cases where A, B, and C slanted differently. Okay, that's a very quick summary about the terminology here. Okay, trinode restructuring step. Okay. Okay. Let's now take a look at the right-left rotation. Before that, let's make do some conceptual clarification. Okay, this will be a double rotation. Okay, let's see. To start with, we have A, B, and C. Right? We got these three nodes. The way they slant goes like this. First of all, they slant to the right here. And then from B to C, they slant to the left. Okay? Like that. Ultimately, we somehow want to promote the node C here. So when you do actually double rotation, you're not focusing on just the middle node. You're more focusing on the lowest node because somehow you want to promote it 2 levels. Each rotation is going to promote 1 level. Okay? When you do the single rotation, you're only promoting the middle node up 1 level. But now when you do double rotations, you're promoting the lowest node here 2 levels. Okay? So the C here is going to be promoted. This one here is going to be promoted. Okay, so this one here to be promoted up 2 levels. Okay, you can think about we are first of all going to rotate C to the right so that it becomes over here. Not yet the root. And then from here, we're going to promote that another level up, but to the left. So it has now become the root. Right? You can see we're doing the right and then the left. That's why it's called right-left rotations. Okay, let me repeat. Okay? So the goal here is to promote the lowest node here up 2 levels. But what should be the direction? It really depends on when C wants to go up to the root, what should be the rotation? What should be the direction? For C to really go to the root, to go to A, you want to go, first of all, go to the right and go to the left. Okay? So for C, first of all, if for C to go to B, it's really go to the right. And for B to go to A, it's really go to the left. It's kind of opposite to which child it belongs to, right? You can see here, even though it says left, but B is a right child of A. It's the opposite because we're going from down to up rather than from up to down. And also C here is a left child of B, right? So now we're just going from down to up. From C to B, going to the right. From B to A, going to the left, right? So we do a right rotation first, and then we do a left rotation. So here, from here to here, it's a right rotation. Right rotation. And then from here to here, this is a left rotation. But just remember, the target is really the C. That one hasn't changed. C is always our target. Okay? Eventually, C is going to become the root. Okay, one more thing to mention, that in order traversal that we are doing, before the first rotation, before the second rotation, and also after the second rotation, the in order traversal are just the same. We're just doing restructuring, right? So the in order traversal will just be in order traversal will just be T1A, T2C, T3B, and then T4. All right, so that's really in order traversal, right? T1A, T2C, T3B, and T4. After the second rotation, I still have T1A, T2, T1A, T2, C, the middle, and then T3B, T4, T3B, T4, right? The same in order traversal. Now, when you do the example, right, do you really have to somehow separate between the two rotations? When I say I want to do a right-left rotation, do you really have to somehow say, okay, I'm here now, I'm going to somehow redraw the tree so that I will do a single rotation, see what it is, and I'll do another left rotation. You don't really need to do that. Okay, I'll show you. There's a shortcut to it, which is acceptable, right, for exercise we're going to do. You can simply think about this intermediate stage is really after the first rotation. Now you can think about we are doing two rotations at one go simultaneously. Think about C here is just going to become the root. And from there, how should we restructure A and B accordingly? Because we know that when we do the initial in order traversal, it's going to be A will be 1, and then C will be 2, and then B here will be 3, right? So A will be 1, and then C will be 2, and then B will be 3. We know that when we do the in order traversal, it's going to be A followed by C followed by B. So if we want to ultimately put C here, it's going to be A and B falling underneath it. Just follow the in order traversal. I think that'll be just a shortcut for you. I think that's acceptable. All right, think about this kind of abstract, steps over here. And when we do the example, we're going to follow just that. Okay. Okay, let's now do this example quickly, and then we'll take a short break. Okay. All right, so guys, you're going to start with, why don't you draw? Okay, I'll give you the slides, and I'll draw something on this on my iPad as well. So now we are doing the right-left rotation. Okay, can you please construct a tree like this by inserting the sequence of key over here. 44, 17, 78, 32, 50, 88, 82, 95. At the same time, annotate the tree to see if that's balanced. It'll take about 1 minute. Okay, I'm almost done. Okay, at least you should get something like this, right? At least for the structure of the tree. Okay, just make sure that's the, before you do annotation. And then we got 0, 0, 0, 0, 1, 1. 0, 0, 0, 0, 1, 1. 0, 1, 2. 1, 1, 2. 1, 2, 3. 2, 3, 4. Of course, this first step got to be right, so double check, right? All right, so what we want to do is we want to insert 85, okay? And you can go ahead and do it, 85. Of course, you may want to redraw the tree. It's up to you. So that would be B. So from A to B, we basically have inserted 85. Okay, insert 85. And 85, where should it go? Anyone? Anyone? Under 82, do you agree? Okay, should it put it to the right or to the left? Right. Okay, awesome. Right, that's easy. I'm just checking. Good. Right here. 85. 85. And then we got 2 external nodes right here. And to answer whether or not it's balanced, of course the previous one, it is balanced, right? It is balanced. And this one, most likely unbalanced, otherwise, there's no rotation to be done. So let's see. Let's update the heights. 0, okay, sorry. My pencil is a little bit loose right here. There we go. So we got 0, 0, and then we got 1. 0, 1, we got 2, right? 2, 1, we got 3. 1, 3, we got 4. 2, 4, we got 5. First of all, let's update the balance first. The height first. And then we are ought to identify the very first node that has become unbalanced. That means the very first node, the lowest node where it's the height of its 2 children is more than 1. The difference is more than 1. Okay, let's see. So we see that. So the difference between, so I'm going to follow the ancestor path, right? So let's highlight the ancestor path. 85 is what we just inserted. Ancestor path goes like this: 85 to 82. 85 to 82, then to 88, and then to 78, and then to 44. Okay, that's an ancestor path. Let me just remind you, you really have to go with the ancestor path. Ancestor path of 85, that's inserted. Okay, let's now take a look. So 0, 1 is okay. 0 and 1. 2 and 1, 1 and 3. That's where the trouble is, right? Okay, 1 and 3 is the trouble. So what we should really make sure, let me highlight that. So 1 and 3, the difference is more than 1. So the difference is 2. That means this node here is the very first node. That's unbalanced. So we call this the A, all right? And then we call its child in the ancestor path B. And then the child here, C. So as you can see, they don't slant the same way. To the right and to the left. Right? That means we want to ultimately promote the C here up by 2 levels. First of all, to the right, and then to the left. So we got to do a right-left rotations. All right? So before we do that, I want to just remind you again the rule, right? It's always something you can just draw right away quickly for yourself. Okay? Let me do one more thing. Okay, so you can, what about the subtree, right? So let me just highlight the subtree for you. So for A here, this one is interesting. The subtree for A is right here. This is T1. And the left subtree for B is right here. Oh, sorry. The C here, right? The C is right here. The C's left subtree is here. This is T2. And the right subtree for C is here, T3. And then the right subtree of B is T4, right here. Okay, I'm going to redraw the tree, don't worry, in the last step. I just want to show you how you can identify T1, T2, T3, and T4. Okay? Let me set it aside. Okay? So what we have here is we actually got A, and then B, and then C. Underneath A, we got T1. Underneath C, we got T2, and also T3. Underneath B, we got T4. That's what we have, right? And that's exactly the pattern that we saw earlier, right? T1, T2, T3, T4, right? Okay? And this is a shortcut I want to show to you. We know that we want to ultimately promote C, first of all, do a right rotation and do a left rotation. Okay? Let's now do all at one go. Okay? So think about we're going to somehow rotate C twice. We're going to do a right. You can think about, first of all, you're going to do a right. And then you're going to do a left. Right, left rotations on C. What that will do is it's going to put C in the root. So we're going to get C here. Underneath it, we know that when we do the in-order traversal, T1A and then T2C, right? And then we get B. So A, C, B. So we got A, C, and B. Okay, so we got A here and B here. Underneath it, we got 4 subtrees. Well, exactly, it's going to be T1, T2, T3, T4. All right, so that's the ultimate thing we're going to have. Okay, over here. Okay, that's something you can maybe draw on your sketch paper. It's not part of the answer. I think it's going to help you. Okay. So what we're going to get is, so let's now try to do that. Okay, so let's now get C. Okay. You know what? How about this? Let me just make this one here much smaller. I can create a little bit more space for myself. Okay, so there's some hints for you to look at along the side. Right here. Oh, sorry. Right here. And let's now go for right-left rotation. So what we got is right-left rotations on C. Okay, so now we got a third step right here. Okay, we do something very similar as before, but let me just redraw the tree to be 100% clean. Okay, so I got 44 here. I got 17. I have 78. And then I got external node here. And then we got 32. And we got this. Of course, the majority of the tree is not going to change. It's really that particular subtree that's going to involve A, B, and C. It's going to change. So 78, we got 50. And then over here, right here. And then we got 88, 82, 95, and then we got 85, right? So we got 85, and then we got this, and we got this. And under 95, we got this, and then we got this. Okay, that's a new tree after the insertion, okay? And we know that this is A, this is B, and this is C. We also know that this part here is T1. For now, I'm just going to annotate it so it's easier for you to see. T1, and just this part here. Oh, sorry. And then we're going to get just this part. Oh, I beg your pardon. I actually put A, B, and C, right? Yeah, you got to be careful. Yeah, my bad. C here, because you're trying to follow the ancestor path. So C is 82, not 95. Right? I made a mistake. Okay, just be careful. Okay, so C here should be 82, right here. Okay. Again, the mistake I made was I labeled this 95 here to be C. Not the case. Because you look at the original tree here, it should really follow along the ancestor path. So now that's why you got A, B, and also C. All right? Be careful. All right, so and then I got the T2 over here. T2 over here. And then we got T3 over here. And finally, this whole thing over here is T4. Okay, just be sure. Okay, all good. So it is this particular subtree that we are going to have to restructure. All right? Let's see how we can do that. Okay? And I'm going to do something very similar. Let me just set it aside. I'm just going to detach conceptually this part here. Of course, if you do it on the paper, you cannot really do it, but just for illustration, okay, like that. I detach it. How do I reconstruct it? The new root is going to be the C, right? The new root. So C, A, B. Let's do that first. So I got C here, right here. I got A right here. Okay, I'll put a little bit up. So C here, and then A here, and then I got the B here. Let's reconstruct just this part. C to A, C to B, right? And then underneath it, I should really get T1, T2, T3, T4, okay? So I got T1 should be right here. T2 should be right here. And T3 should be, oh, actually be careful. So T3 should be here, okay? I'll move this a little bit up. Good. And T4 should be right here, okay? And how do we link them? So 78, the left should be T1. The right of 78 should be T2, right here. Okay, I'll move that up a little bit. And then the left of B should be T3. And the right of B should be T4. Just by looking at this particular subtree, what do we see? Itself is a binary search tree. Okay, how do we see? 50, 78, 82, 85, 88, 95 in order, sorted. All right? And all we got to do is attach this one here to right here. Okay, let me try to align them a bit. Okay? Like that. Okay, I can put 44 right here. Okay? So think about it's right here, and then it's here. So this part here is really the only part that's impacted, really. Just this part. All right? as a final answer. Now, let's annotate the heights just to make sure. Okay, so what we have is we got 0, I got 0, 0, 1, 0, I got 2, right? So here I got 0, 0, 1, 0, 0, 1, 1, 1, I got 2. 2, 2, I got 3, right? So 0, 0, 1, 0, 1, 2. 2, 3, I got 4, right? Double check, balanced, okay? So the big picture here is pretty clear. You just got to see, once you identify A, B, and C, just to see how they kind of slant. If they slant the same way, you either do a left or do a right rotation. But if they slant differently, you're going to do double rotation. How should you do a left-right or right-left? Take a look at the lowest node, that like a C, and see how you can promote it 2 levels up. That's how you see it. All right, questions? Good? Okay, exercise for you will be this one here. Right? I'll give you the answer for this left-right rotations, and you can take a look at this example here. Take a look, okay, and see how to do it. Okay, why don't we take a very short break by taking attendance, and then after that we can do a little bit deletion. Okay. All right. So we're basically done with the insertion, also the relevant rotation. That's what we have done. So I think now it's for the completed story, we should talk about deletion. Because whenever you want to have your binary search tree, the way to grow or shrink the tree is by insertion and deletion. So let's see how the deletion is going to be done. It's going to be done in a very similar way, but the complication is to really do a removal from the binary search tree itself will actually have more cases for you to consider. It's not just about whether the key exists or not. It's not just that. You got to see more. There can be more considerations. Okay. It's actually on the slides. I'll just show you where you can find them. I'm going to do some example together with you, and also highlights the step you should really watch out for. So you should look at slide number 14. All right. Slide number 14 is really about all the 4 cases you have to worry about for deletion. We're going to go over also one at a time as a review. Okay, that's kind of important. So look at slide number 14 when you do the study. And another one, which I may not get to today, but we can do that in the tutorial when we get to the exercise. So you will see that when we talk about deletion, right? Let me just show to you right here. So the one to look at is slide number 32. All right, so this is second slides. So this slide here, while the previous slide I showed to you is about how you can do deletion. There are 4 cases. And now, after the deletion, what kind of rotation should we do? And that's another like an algorithm that you kind of want to see exactly how to do. So we're going to go over this one as well, but this one maybe a little bit later. But let's just review how to do deletion. Let's do that first. Okay, and then once this is done, this part here I'll guide you about how to understand this algorithm here. Okay. Okay, for deletion. Let's go over the principle one by one, case by case. Okay, so there are 4 cases in total. To be fair, it's more like case number 1, 2, and 3, but for case number 4, it has 2 subcases, either 4.1 or 4.2. So we're going to go over 5 cases in total. So 5 examples. Okay, we'll see how many we can do today. Right, so in order to delete something, you got to make sure the thing you want to delete may or may not exist, right? So part of it, you still want to do a binary search right here, okay? So you can see this is the binary search that we have to do. So the binary search we do is going to take the starting node. Oh, sorry. I thought I closed that already. Okay, sorry about that. Okay, so when we do the binary search, this will be the root, the starting point. And the key is something we want to search for. So that will be the key of entry to be deleted. Okay, so that's what we're going to do. And when you actually call this binary search routine or method, it's going to return to you P. And a P here, according to what we learned from the binary search, it can either be internal or external, right? If that's internal, that means the key exists. If that's external, that means the key does not exist. Okay, so case number 1 is actually what you will hope for, right? So you can see for case number 1 here, if the node that's returned is simply external, that means what you want to return, what you want to delete doesn't even exist in the tree. Nothing to delete, do nothing. Awesome, okay? But that's one case. Let's see this case right away, okay? So let's say here, we have the tree. You want to delete the key 31. We're going to do a binary search. So 31 less than this, so go this way. And 31 larger than that, so go this way. And then 31 less than this, so go this way. And then 31 larger than that, go this way. And 31 larger than that, go this way, right? So this is something that's going to be returned. So the key doesn't even exist, nothing to delete. It would be as if you simply want to delete this external node, which is going to do nothing, right? So nothing to do. That's case number 1, simple. So key does not exist. In which case, do nothing. Nothing to delete, basically. Okay, awesome. All right, let's see case number 2. For case number 2, the key, let's see. The key actually exists, first of all. So this one here, we basically say P itself is internal. However, both of its child nodes are external. What does that mean? What that means is, for case number 2, what we are saying is, the node that we want to return, or we want to delete is called P, right? Let's say that's a node we want to delete. That's internal. However, both of its child node is simply external. This is also very easy to delete. Basically, when you delete this particular node, you don't need to worry about handling these two external nodes because they don't store any key anyway. You can just delete it without worrying about the consequence. All right? So there's no, once I delete this node here, these subtrees are called orphan subtrees. But in this case, these are just external, so you don't need to worry about them. Okay, so just remove the P itself. Okay, let's see. And the question is it still a BST? We're going to see. Okay. Let's now take a look at case number 2. Okay, so we start with 44 again. So 44 is less than 80. So we go to the right. And 80 is less than 88. So we go to the left. So 80 is larger than 65. So go to the right. And 80 is less than 82. So go to the left. And 80 is larger than 76. So we go here. Right? So this is the node that we want to delete. And according to the algorithm here, the node that's being returned from binary search is called P. So we call this node P. Okay? P is something we want to delete. And it's matching case number 2 because these two external nodes are, or these two nodes are simply external nodes. Right? If you think about the in-order traversal, what are we doing here? So let me just try to narrow down the in-order traversal that we can do. Why don't we just look at just this particular part? Well, actually, how about this? Let's now try to look at this particular subtree. Just this one here. Okay? Let's now consider what's the in-order traversal for that. That one there is going to be, okay, start with 54. Okay. We start with 54. And then 65. And then 76. And then 80. And then 82. And then 88. Right? There might be keys after that and also keys before that. Right? We only focus on that particular subtree. That's the in-order traversal. And we want to delete 80. So after that, 76 is here, and also 82 is right here. All you do is just delete it. Basically, you can just basically turn this one here into some external node. That's all you do. So the right child for 76 right here is not going to be set to some external node. That's all you got to do. And the reason that this will work is because if you look at the new in-order traversal, I'm just deleting 80. So I still got 76 followed by 82. Whether or not it's still balanced is another story, right? We're going to handle the balance rotation by another phase. This phase here, just want to delete. Okay. All right, any questions? Good? Okay, good. Let's do case number 3, okay, at least for today. So for case number 3, what we have is this. So what we have, we still get P, but we only got one of the child nodes is internal. That means one internal and one external child. That's what we have, right? So for case number 3 over here, what we have is, we have the P that we want to delete. One of the nodes could be left or could be right. Let's say it's left, it's internal. But the right child over here is external. Okay? And then there might be something underneath it, right? So in this case, how do we somehow delete P? In this case, you may have to worry about, oh, what about, if once I delete this, what about its left child? Because it's internal, right? So I got to worry about that. So we're going to see exactly what to do. It turns out, it would just be okay. Just return. So we talk about something called R. I'll show you what R is in the algorithm. Okay. The R is the child of P that's internal. So this is R right here. Okay, this is R. So what we are saying is, all you do is, you can simply replace the value of P just by R. But we'll see exactly how to do that, right? That's what you will see in the algorithm. Just replace the P by R. But how do we replace it? We'll see. Right? Okay, let's see. Let's now take a look at case number 3. Right here. So we want to, let's say, delete an entry with the key 32. Right here. Okay, how do we delete it? So 32 is less than that. So we go to the left. And 32 is larger than 17, go to the right. And 32 is right here, right? According to the algorithm, this is called P. You can see its child nodes, one is external, the other one is internal. That's why we are matching case number 3, right here. Okay? And we call the internal child R. That's what we have. So this is called R. Right? So what should we do now? This case here is not too bad. Okay? Basically, what we can do is, there's several, you can think about conceptually. We want to somehow replace the 32 over here just by the 28. How exactly do we do that? Okay. So we may have to somehow, first of all, delete this link. And then 17 over here is going to set a link to be this one here. Okay. And then this one here might just be garbage collected at some point. We don't need to worry. You just stay disconnected from the tree. Okay, 2-step. So this will be step number 1. You want to get here, and step number 2. Right? That may be something like a Java code you can think about. Yeah.
Do we need step number 1? Like if I just said 17.next is equal to 28, like there's no reference to.
Yeah, I just want to be a little cleaner conceptually. Just want to make sure it's completely disconnected, right? Just diagrammatically. You want to make sure that one there is not a child nodes for 32 anymore. So that's why I want to do that. Yeah, may not be programmatically necessary, you're right, but we can just make it cleaner, right? Good. Yeah, awesome. It's a good question. Yeah. All right, so that's what we're gonna do. And how do we justify this? Very quickly, okay? So once this is done, conceptually, this will be gotten rid of. Okay, so this one will be done, right here. So now if you think about it in order traversal again, right? You want to make sure after each deletion, the in-order traversal is still going to give you some sorted sequence that is so necessary, right? Let's say this part over here, right? Okay, let me finish this part here and then we are done, okay? Just bear with me 1 minute or two. So the in-order traversal before the deletion. The in-order traversal before the deletion. So we got 17 here, followed by 21, followed by 28, followed by 29, and followed by 32. Okay. So what we want to do is we simply just want to get rid of the 32. That's what we want to do. Right? Is this actually the new in-order traversal we'll see? Indeed, right? If you look at that, it's going to be 17, followed by 21, and then we go to 28, and then we go to 29. That's exactly right. Okay? Because now the 28 has now become the right child of 17. That's what you have. Okay? Just make sure you follow that one there. Okay? So now we got case number 1, 2, and 3. Okay? So I would suggest in this week tutorial on Friday, I will do very quickly about case number 4, and then we'll talk about how to do the conceptual rotations to really fix the balance after deletion, right? There'll be some interesting case to see. And then we'll talk about some Java implementation as well, right? So please make sure you come to Friday, and then we'll talk about things, okay? Thank you, and I'll see you on Friday.